Welcome to Data Science 1, Probability, more on sums of random variables. So items to remember, we need to know what independent identically distributed means, Bernoulli random variables, Poisson random variables, and not really the others yet. But we're going to get those in the next video. All right, so IID, independent identically distributed, means that we are using the same sample space. We're going to get all the random variables are going to elicit the same probability distribution, and the probability distributions are going to be having the exact same parameterization. So everything's going to be the same, and none of the experiments interfere with any of the other experiments' outcomes. We were able to estimate the mean parameter. We found the expected value of x bar was mu of x. We can measure the variability around it. And this works well for evaluating the mean, and we actually had the central limit theorem in there. But it gives us an approximation. What if we're interested in other items than just the mean? So here's a simple one. So suppose x1 through xn are IID f of x, and they have a mean and a variance. Let f of x be, instead this case, Bernoulli with the parameter p distribution. So our expected value of each one of these, the probability of success, and the variance is p times 1 minus p. What is the distribution if I wanted to just add up some Bernoulli random variables? I don't really care about dividing by n. I just want to add them up. Because this is quite common, by the way. And it turns out that it's binomial NP. So super easy. And we can get its expected value and variances pretty easy. Now, this is not an approximation like the central limit theorem. Central limit theorem says if you get enough observations, and then things will approach normality. Here, we don't need that assumption. N could be 2, and it works. So it's not an approximation. And if you think about it, this really does make sense. The binomial random variable is the total number of successes from n Bernoulli trials. I put the word total in there because before we just said it's the number of successes, right? But here we're totaling the number of successes, and if you think of the word total, you think about adding, which means you think about summing. All right, so here's a quick example. Mohamed Salah has taken 47 shots this year in the 2021 season as of this recording date, which is December 22nd, 2020. I got the information from this website, and there have been 47 shots taken and 13 goals. Okay, so there have been 47 Bernoulli trials. A single shot is a Bernoulli trial, and there were 13 successes, right? So this should be pretty easy. But we want the distribution of the sum of the successes. Hence, the probability of that sum is going to be a binomial 47p. And here, if we knew p, we could do a lot of stuff. But at the moment, we don't know p. And we're going to get that in a future video that's close by. But we're getting really close to being able to actually doing some serious inference. All right, what about the Poisson distribution? So we did the Bernoulli. Well, again, same setup, except this time we are going to be Poisson lambda. So our expected value of each one of these, since they're IID, has the same parameter lambda. The variance is lambda. What is the distribution of the sum of these? Well, kind of probably can guess it. It's just n times lambda, because they're going to be exactly the same time intervals and everything. The expected value is going to be n lambda. The variance is going to be n lambda. It's not an approximation again, so keep that in mind. This is the exact distribution, so we can calculate exact probabilities from it. And this does make sense if you think about it. I'm counting the number of successes over an individual time period. Well, if I'm adding them up, I'm just making the time period longer. So I would expect if the probability of success for the Bernoulli trial stays the same, or my rate here, lambda, stays the same across all of them, it should just be multiplying it times the number of times that time or space that I have. So it does make sense. So here, let's think about a quick example because we don't want this video to run real long. But here's a shopping market stall. Every day, Sareb counts a number of people who come to her shop in a market. Okay, not whether they buy, just who's showing up. If xi is the count for one day, and each day seems to be the same as any other day, what is the distribution for the number of people who will shop there in a week? Well, It seems like it'd be obvious that just 7 times the average would be that. But it comes with a Poisson distribution. And that's what comes in really handy here, because it's an exact distribution. Oh, if we were to know lambda, we could make some serious tests and we could do some really good stuff. And that's where I'm trying to use this as a teaser to make you want to know these parameters, so that when we get to estimation, you'll be like, and also testing, you'll be like, oh, this makes so much sense. All right, so here we made this assumption. And each day seems to be the same as any other day. So there is no variation in the weeks. But what if there were? Well, it turns out with the Poisson, if we had lambda 1, lambda 2, up through lambda 7 are the mean counts for each day, then the distribution would change, but it's still Poisson. However, instead of just being n times lambda, we're just going to add up the number of lambdas, okay? Not the number of lambdas, but add up the lambdas themselves. But this makes our problem worse, because now we have 7 lambdas that we don't know. But not to worry, we will figure things out and how to work with these in the near future. All right, so far, we played around with the Bernoulli trial and found out that if we sum them up, it's binomial. If we have Poisson experiments that are IID, we end up with Poisson. And if we just have independent Poisson experiments, we end up with Poisson. And I have a pun here, so just roll with it. If you don't know what a pun is, it's a play on words. So we will go over some more in the next video. And we'll talk about the normal distribution and the exponential distribution there. So see you there.